Okay, hi everybody. We are on to our next lesson in this probability distributions unit. We're on 6.3 and they are called geometric distributions. So the first thing I want to talk to you about is that last topic we talked about binomial distributions and how easy it was to use the binomial theorem and Pascal's triangle to calculate distribution probabilities. Well, we're going to use that same principle here on geometric distributions because they still apply to Bernoulli trials. And if you remember what a Bernoulli trial is it's either success or failure. Either you succeed or you fail. However, the biggest difference in a geometric distribution is not how many successes you get. That would be a binomial distribution. I could have 6 out of 10 correct or 2 out of 10 correct. But instead, x, the variable x, is the number of trials before you get your first success. So it's not how many, you're only getting one success technically, it's how long you have to wait until you get your first success. So, examples might be board games in which you cannot move until you roll a double. That word until is very important because that means nothing's happening until this occurs, a double. Sporting events in which the winner is the player who scores the most points before missing a shot. So the first time they miss, their turn is over. Determining the time until a particular piece of equipment fails. So it is succeeding 5 times, 6 times, and finally it fails. We're waiting for it to fail. The number of trials before you get a success is called the waiting time. And you're going to hear me talk a lot about waiting time during this topic. So we still have trials with 2 possible outcomes, success or failure. That's a Bernoulli trial. We have probabilities that do not change from trial to trial. That means that we have independent trials. And we have 2 probability formulas for that. So the probability for a geometric distribution is given by q to the x times p, where q is still failure, probability of failure, p is success, and x is the number of times you need to wait. And if that's the case, then let's try example 1. I'm going to come back to this other formula down here in just a second, but let's try out this formula here, q to the x times p, and why it makes sense. If the probability is 0.75, that an applicant for a driver's license will pass the road test on any given try, so it looks like they've got a 75% chance of passing the road test. What is the probability that an applicant will finally pass the test on the 4th try? Well, if they finally pass the test on the 4th try, what must that have meant for the first 3 tries? You guessed it, they failed the first 3 tries and they finally passed on the 4th one. Okay, well that means in this case that P, the probability of success, that means they passed the test, because that's what we're waiting for. We're waiting for them to pass the test on the 4th try. Passing the test is 75%. Q, failure, must be 25% chance of failing on any given try. And x here represents the number of times we must have failed before we got our first success. And we must have failed 3 times in a row in order for this to happen on the 4th try. So what is the probability that our random variable x is equal to 3? Well, that is 0.25. That's the chance of failing, raised to the 3. That must have happened 3 times, multiplied by 0.75. That's what happened at the end. It capped it off. That was our final ending. So in other words, this would have looked like on a tree diagram, fail, then fail, then fail, then pass. Fail, 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 pass. That one outcome in the tree diagram that represents fail, 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 pass. So 0.25 raised to the 3 times 0.75 gives me 0.0117. or about a 1.17% chance of that happening. So you can see that this represents a waiting time. What are we waiting for? We're waiting for this person to finally pass the test on the 4th try, which means they must have failed the test on the first 3 tries. Now let's take a look at example 2. Jamal has a success rate of 68% for scoring on free throws in basketball. That means he's a pretty good free throw shooter. What is the probability that he misses the basket on his 3rd throw? So what is it that we're waiting for? Are we waiting for him to make his first basket, or are we waiting for him to miss the basket? And it looks like here we're waiting for him to miss the basket. So it's like we're the opposition, we're his opponent. We're waiting for him to miss. We want him to miss. So him missing is technically a success for us. And him missing here must be a 32% chance of that happening. So 0.32 is the chance that he misses. Q here, failing, technically means he made a basket. And he's got a 68% chance of that happening. And what is X? Well, if he's going to miss for the first time on his 3rd throw, that means he must have made the first 2 baskets. So we want to find the probability that X is equal to 2. That's the waiting time for this question, X equals 2. And that means that we need to multiply the number or percentage chance that he made the first 2 baskets, 68% chance of making a basket, that happened twice. And finally, he missed on the last one, on the 3rd throw, 0.32. Technically raised to the 1 if you like. And that answer is, wait for it, 0.14796, so 80, or approximately 14.80% chance of him having to wait, this opponent, I should say, wait through 2 made shots before he missed on his 3rd throw. Part B, what is the expected waiting time before he misses the basket on free throws? So this is the, on average, how long should we have to wait before he misses the basket for the first time? Well, if he has a 68% chance of scoring, I don't think we should have to wait too long, but we'll have to wait through a couple because he's pretty good. 68% is a pretty good free throw rate. Well, the probability, the expected value here, given the formula, and I didn't go over it yet, but I'll go over it quickly now. EX is equal to Q over P. That's the short form or the shortcut, Q over P. So EX is equal to Q over P, but remember, our failure here technically means he made a basket. And our success, probability of success, P, means he missed. So it's 0.68 to 0.32, and 0.68 divided by 0.32 means that we have to wait through an average of 2.125 shots before he misses for the first time. So remember, it's an average, and this is like over many trials. And if that's the case, if we did this many times, we'd have to probably wait about 2.125 shots before it would be our turn, before he misses for the first time. And that makes sense to me because he's a pretty good shooter. We would have to wait that long. I want you to think as an exercise, what if this top number was 99%? If this was 99% and on the bottom success is 0.01, well, 99% over 0.01 means we'd have to wait through 99 shots on average before he misses for the first time. That makes sense because he's a really good free throw shooter. He makes 99% of his shots. I'll go on to example 3 in the next video.